Hello students, welcome back to Math 332 Linear Algebra. In this video we are going to look at section 1.3, which is on matrices and matrix operations. All right, let's get to it. All right, let us start by looking at the objectives for these particular sections. So in these sections, you would need to know how to do arithmetic on matrices, which means you need to know how to add and subtract matrices as multiply a matrix with a scalar determines when two matrices are compatible in terms of matrix multiplication and actually how to compute matrix multiplications. And also, more importantly, something that we're going to use a lot in this course is to notice that matrix multiplication can be actually expressed as a linear combinations of its rows and columns. And this is something that even if you have taken algebra and have seen matrix operation before, might have missed that because it was never really been emphasized at a high school level. So this is something that you want to pay attention to. And you also need to be aware of some of the special property of matrix operations. Okay, so let's get right into it. So what is a matrix? So matrix is basically arrangement, a rectangular array of numbers, symbols, expressions, or doesn't really matter, whatever it is that is put in this form. So this is what we call a matrix. So sometimes you use a square bracket, sometimes you use this bracket, so it doesn't really matter. So you can see that sometimes we write our matrices like this, sometimes we write our matrices like this. It doesn't really matter. What it really matters is that you have to notice that for every matrix, we have the concept of a row of a matrix. So this is the row of the matrix. This is the first row of the matrix. This is the second row of the matrix. And this is what we call the first columns of the matrix, the second column of the matrix, so on and so forth. And the way we index the entries or the elements of a matrix is by first identifying the row and then the column. So Aij, so sometimes matrix is also written like this. This means that you have a matrix consists of elements, which looks like this. And the first indices here is to indicate the position of the row, and the second one here is to indicate the positions of the column. So as you can see right here, is that this 2 1s means that this is an entries in the matrix, which is in the second row and the first columns of the matrix. So the A2M right here means this is the second row and the M column. And this one right here means that this is on the n row and the second column. So every entries of a matrix can be identified like that. And another thing you need to know is that for every matrices, we also identify by its size. So the size of a matrix is indicated by the number of rows times the number of columns. So it's not really times. We say this is like this is an n by m matrix because it has n row and m columns, and we also write like that. Okay, so for example, this is what we call a 3 by 1 matrix. We never really multiply them. This is just how we write them. So 3 by 1 matrix, 3 rows and 1 column, and this is also known as column vectors. And this one right here is a 1 by 3 matrix, which is also known as a row vectors. This has special names. This is what we call a square matrix. Square matrix is a matrix which has the same number of row and the same number of column. In this case, this is a 2 by 2 matrix. This is what we call a rectangular matrix, which is matrices that are not square. So this is what we call a 2 by 3 matrix. And this is what we call a 3 by 3 square matrix. And this matrix is special. This is what we call the identity matrix. And this is a 2 by 2 matrix, which is also special. This is what we call the zero matrix. And so you kind of have an idea what matrices is about. So matrices basically just arrangements, a rectangular array of numbers, symbols, and stuff like that. You have size of the matrix, and we indicate the entries of a matrix by identify the rows and then the column. And so that's basically what you need to know for matrices. And now we are going to look at the arithmetics algebraic operations for matrices. So remember that last time when you first learned how to what are numbers when you are like in preschool and stuff like that, and the next day your teacher would teach you how to add or subtract those numbers, and then how to multiply, how to divide. Same thing when you are in high school, you learn polynomials, and then the next day you'll learn how to add or subtract polynomials, multiply polynomials, even dividing polynomials by long divisions and stuff like that. So same thing we're going to do is that once you know about matrices, we want to talk about the arithmetic, the algebraic operations that you can do on matrices. So before we do that, let's talk about what happens when two matrices are equal. That's pretty straightforward. Two matrices are equal to each other. First and foremost, that they have to have the same size. So this is a 2 by 2 matrix. This is a 2 by 2 matrix. They have to have the same size. And we say P and Q are the same if all the corresponding entries are the same. So this is 1, this is 2, this is 4, this is 4, and this is going to be 7. So P, matrix P and matrix Q are equal to each other if this matrix P here, this X here is 7. So this is something that is pretty straightforward. So this is the concept of equality of matrices. And how do you add and how do you subtract matrices? This is also pretty straightforward. In order for you to be able to add or subtract matrices, again, the first thing is that they have to have the same size. So matrix A here is 3 by 4. Matrix B here is 3 by 4. So they have the same size. So we can add and subtract them. And the way you do it is pretty straightforward. You take the corresponding entries right here and add them. That makes it 6. You take the corresponding entries here and add them, and this makes it 3, so on and so forth. So for subtraction, it's also the same. You look at these entries right here and you subtract, you get this. You look at these entries right here, you subtract, you get this, so on and so forth. So that's pretty straightforward. For scalar multiplication, that's another type of multiplications for matrices, which is like you take any matrix of any sizes, and you basically just multiply a scalar, which is just a number, to the matrix. Like say, for example, this is matrix A, and 2A will be multiplying 2 to every single entries of this matrix A. So this is pretty, again, straightforward. And this is your matrix B. So if you multiply 1 over 3 to B, you will have to multiply every entries here by 1 over 3. That's the reason why 1 over 3B is given like that. So for matrix addition, subtraction, and scalar multiplication, that is pretty easy. And for matrix multiplications, though, things are a little bit more subtle, but not too bad. But I have to tell you how you can actually multiply matrices, two matrices, not just a matrix with a number. So first of all, you will have to make sure that two matrices are compatible in terms of multiplications. What it means is that if this matrix A is of size n by n, this matrix B has to be of size n by k. These two inner numbers have to be the same before we can multiply them. So this has to be same. Then we will say that this matrix AB are compatible in terms of multiplications. And then after that, this matrix AB as a single matrix, as one matrix, not as two matrices. This single matrix AB will be of size m by k. So the outer number here will give you the size of the matrix after you multiply them. Okay, so for example, this is a 2 by 3 matrix, and this is a 3 by 4 matrix. So because of these two numbers the same, so we say that these two matrices are compatible in terms of multiplications. And after you multiply them, this matrix is going to be of size 2 by 4. You have 2 rows and 4 columns. So how do we actually multiply them once we realize that they are compatible? So what happened is that when you take a row of a matrix and a column of a matrix, when you multiply them, what you do is you take this number and multiply this number, this and this, again, this and this, this and this, line them up, and then sum it up. So this is what happened when you encounter a row of a matrix and a column of a matrix, and this is how you should multiply them. And so apply it to matrix multiplication is that once you have these two matrices and you determine that they are compatible in terms of multiplications, what you need to do is you take this first row here and multiply this column. This will give you the entries right here. Okay, so let me make this very, very clear. So one way you can do this kind of multiplications is to look at the size again. So this is 2 by 3, this is 3 by 4. We know they are compatible. So the end result will be a matrix of size 2 by 4. So you have 2 rows. and then for column 1, 2, 3, 4. So every entries here will be a number. So this will be a number, this will be a numbers, this will be a number. So we have to determine all these numbers. And the way we determine this number is like this. So this, okay, this is the 1, 1 entry, right? First row, first column. So how do you do that? You take the first row and first column and do this operation right here. So let's do that. So let's fill up this thing right here. So you will take 3 multiply 1 plus 1 multiply 0 and then plus 2 multiply -1 and then sum them up and you will get this number as 1. Okay, so if you want to figure out what is the entries for this particular number here, so this is second row and fourth column. So you take the second row and fourth column, and what you do is you follow this rule. So you take 5 times 3, okay, and then you take 0 times -2, right, and then you take 4 times 4, all right, and sum it up. So this gives you 0, this gives you 15, this gives you 16. So altogether, this will be the number 31. So that's how you multiply matrices. So if you need to figure out what is this particular entries right here, so what you do, this is the first row and then the third column. So you take first row and third column and follow these procedures to get the numbers. So if you have computed all these numbers, all this, you will get the matrix which is have these entries 1, 26, 1, and 15, and then you have 1, 35, and then you will have 2 and 31, and that's how you multiply matrices. Okay, so matrix multiplications is a little bit different, and that is how you actually multiply matrices. So matrix multiplications is going to be defined this way. First, you have to identify whether or not they are compatible, and then after that, you will have to multiply matrices like this. Okay. Okay, so this explains why in the previous videos when we have equations 2x plus 4y equals to 1 and then 4x minus 3y equals to 2, now you see why this particular system of equations can be written in matrix form like this. Okay, so remember this is 2, 4, this is called the coefficients matrix. And you will see that the reason why these two systems are equivalent is because when you multiply matrices, you will have to do this, all right? So you get a 2 multiply x and then 4 multiply y and sum them up. That is this. And then because of equality of a matrix, this has to be equals to 1. That's how you get that. This is a 2 by 2 matrix. This is a 2 by 1 matrix. So after you multiply them up, you will have a 2 by 1 matrix like this, which is 2x plus 4y. And then this is equals to 1. All right, so that's the first equation right here. And then right here, this one right here, you will see that this is what happens if you multiply 4 with the x and then minus 3 with the y. So you will get 4x minus 3y and equals to 2. So this one here, again, with the concept of equality of a matrix, this gives you this particular equation right here. So now you know. Now you know in the previous video, if you haven't seen matrix multiplication before, now you know why that when you have a system of linear equations like this system of linear equation can be translated into matrix form like this, because that's basically how we multiply our matrices. Okay, so this is matrix multiplications, and this is obviously something that is very important. So again, take a look at this, and then you will see why in the previous video we'll be able to write the system of linear equation into a matrix form that looks like this. Okay, now there are several things that you need to pay attention to. One of it is that when you multiply matrix A with matrix B, so let me write down B as the column. So this is A, I'm just going to leave it like that. And for matrix B, I'm going to write down the columns like this. This is not how you actually write column vectors. You usually write column vectors like this. This is to indicate this is not a number, but a vectors. But I'm going to use this kind of notations to indicate that this is the second row, the first column and the second column of matrix B all the way to the end column. And you will notice that if you multiply matrices A, B using the way we define, what happened is that the end result, the first column of this matrix A, B, it's actually the same as like you multiply matrix A with the first column of B. And the second column of matrix AB is actually can be written like this, which is taking matrix A, multiply the second column of B, and so on and so forth. So this is something that you should pay attention to. And this is also one of the things that we will be using a lot throughout this course. Okay, so before we move on and talk about another very important consequences of matrix multiplications, let me give you a definitions. So this definitions is the definitions on linear combinations. So suppose we have all these matrices and we have all these numbers. So these are just real numbers, okay? So this particular expression here is known as a linear combinations of all these matrices. So every time when you have a numbers multiply a matrix plus a number multiply a matrix plus a number multiply a matrix, this entire expression right here is known as the linear combinations of these matrices. Okay, so when people say you have linear combination of the matrices, they are referring to this particular expressions. Okay, so now when we have these terminologies, I want you to pay attention to this matrix multiplication. So you have a matrix A. So this matrix A, if you look at the entries, you will see that this matrix has m row and n columns. Okay, because if you count the row, this is first row, second row, all the way to the m row. And if you count the column, this is the first column, the second column, all the way to the n column. So matrix A is of size m by n. And this matrix X. So this matrix X is also known as a column vectors. So remember that matrices of this form is known as a column vectors. So this column vectors obviously is a matrix of size n by 1. So again, we know that because these two inner numbers are the same, so we know that they are compatible in terms of matrix multiplications. And AX will be a matrix of size n by 1. So AX will be also a column vectors. It is going to be of size m by 1, m rows and 1 column. So if you multiply AX, you will see that what happens after you multiply AX is going to be like this. And if you take a look at the first column right here, this is not the first column, I'm saying this particular expression right here, you see that you have all the X1, and if you see right here, you have all the X2. So you can rewrite them as this, okay? And this is what we call the linear combinations of the column vectors. So these are the column vectors. You see that this one right here, so this one right here, this is actually the first column of your matrix A. And you will also see that this is the second column of the matrix A. And this is the n column of your matrix A. So apparently after you multiply AX, which is this expression right here, you can rewrite them. You can factor out the X and rewrite them as this form. And this is what we call the linear combinations of the column vectors of matrix A. So AX can be expressed as a linear combinations of the column vectors of matrix A. So this is something that we're going to be using a lot, and this is one of the particular insights that I would want you to pay attention to. So remember, if you multiply A, matrix A, like this, with the column vectors like this, what happens is that you take X1, multiply this column, plus X2, multiply this column, plus all the way to Xn, and multiply this column. So that is what happened. So let me give you one example. This is a summary of what's going on. This is another way of writing it. This is another way of writing this. So again, I'm writing my column like this. This is the column of your matrix A. And when you multiply them, you are taking X1 of this, okay, right? And then you're taking X2 of this, and all the way to Xn of this. And you can see this is AX and can be expressed as a linear combination of the column vectors. So one example is this. So instead of multiplying matrix operation, multiplying matrices like this, okay, so this is how we multiply matrices, right? Multiply, take this one, multiply this, you will get this particular entries right here. You take this, multiply this, you will get these entries right here. And take this, multiply this, you will get these entries right here. So instead of multiplying like that, you can also see that is equivalent to taking 2 of this column plus minus 1 of this column plus 3 of this column. So this product, this matrix product, this matrix multiplications is actually a linear combinations of the columns, can be expressed as a linear combinations as well columns of this matrix, which we call A. Okay, so this is something that you want to pay attention to. Now, This is what happens when you multiply a matrix with a column vector. So if you multiply a matrix with a row vectors, this is also some things that you have to pay attention to. We're going to use it very, very soon. So the way we multiply this, okay, let's look at how we multiply this. This is a 1 by 3 matrix, which is also known as the row vectors. And this is a matrix of size 3 by 1. So again, you can see they are compatible in terms of matrix multiplications. And then sorry, this is 3 by 3, and then the end result, you're going to have a matrix of size 1 by 3, 1 row and 3 column. Okay, so again, the way we typically multiply them is take this, multiply this, okay, to get this number right here, right? Take this, multiply this, we'll get this number right here. Take this, multiply this, we'll get this number right here, because this is 1 by 3, this is 3 by 3. So at the end, we should have a 1 row and 3 columns. We're going to have a matrix of 1 row and 3 columns. That's how we do it. But again, if you multiply this thing out, you will see that these matrix multiplication give you this. And you can rearrange them. Take all this thing out and put it right here. Okay, and take all this thing out. Okay, take all this thing out. And you can put it right here, and so on and so forth. So you see that actually this matrix multiplications of a row and a matrix is the same as the linear combinations of this row vectors right here. So this is again a number. This is again a number, a number. So these are the row vectors. These are the row vectors. These are row vectors. So taking row vectors like this, multiply a matrix, you can actually express them as the linear combinations of the row vectors of this matrix A. So this is another very important properties that you should pay attention to. Okay, so for example, if you are taking this row vectors, multiplying this, so you will be taking 0 of this row plus 1 of this row plus 0 of this row. So what you get is obviously the second row right here. And this one means that you take 0 of this row plus 0 of this row plus 1 of this row. So you will get this. So this is a linear combination of the row vectors. So you will take 1 of this row and then 0 of this row and then 0 of this row. So obviously you will pick up the first row of this matrix. So this is something that you will have to pay attention to. So right now I would want you to think about this. Okay, so let's pause this video a little bit and let's do this computation and see whether you get it or not. So this is, as you can see, there's a difference. If you multiply the matrix on the left hand side of matrix A and multiply the same matrix on the right hand side of matrix A, things is going to be a little bit different. So let's pause this video for a second and for you to figure out what should your answer be, and we'll be right back. All right, so let's look at the solutions. And as you can see, the way we do this computations is, let's take this row, multiply this matrix. So it will pick up the second row of this matrix. So this is why you have it here. This one right here will pick up, so this one right here, if you multiply this, it will pick up the first row of this matrix A. And this one right here will pick up the third row of this matrix A. So you get that. So this is playing with the row. So when you multiply a matrices on the left hand side of this matrix A, you are kind of like permuting, in this case, the rows of this matrix A. But if you do it here, what happens is that you are going to permuting the column. So this one right here, multiply this, will pick up the second column. Okay, and this one right here, if you multiply with this, will pick up the first column. And this one right here, if you multiply this, will pick up the third column. And so again, if you multiply this matrix on the right hand side of this matrix A, you are changing the column. Right here, you're changing the row, and right here, you're changing the column. So this is the things that we are going to use a lot. Usually, it's not it has not been emphasized even if you have taken a course in involving matrices in high school. Usually, these are the things that your teachers didn't really mention it. So, but we are going to use all this thing a lot in this course, and this is very, very basic consequences of matrix operations, which I want you to pay attention to. Okay, so there are homework problems that we're going to explore on matrix operations, which is different from the usual arithmetics for the numbers. So for example, if you have numbers 2 times 3, obviously this is same as 3 times 2. This is what we call multiplication commutative for numbers. But matrix multiplications is not commutative, might not be commutative for matrix multiplication. So if you have a matrix A, you have a matrix B, this one here might not be the same as this one. So this is one of the very important consequences of matrix operations that is, unfortunately, it might not be commutative. So in your homework problem, you've been asked to look for example that kind of have this non-commutative properties. And also, this is also something that is strange. We're going to explore it in homework, which is that if you have numbers, so remember that in high school, if you have x, y equal to 0, right? So these are numbers. So let's say these are numbers, then you will definitely will be able to say that either x equal to 0 or y equal to 0, right? So this is the key thing on how we solve system of equations, right? So if you have like x plus 1, x minus 2 equal to 0, so you would say x equals to -1 or x equal to 2 because either this equal to 0 or this equal to 0. But this is not true for matrices. You can also find two matrices that is non-zero. These are non-zero. And this is also non-zero. And you will actually get a 0 matrix. This is possible. So this is also something that is strange. So product of two non-zero matrices can actually give you a 0 matrix. So you can't say that because matrix A and B multiply to give you this 0 matrix, so this has to be a 0 matrix or this has to be a 0 matrix. This is no longer true. And another strange thing is that cancellation law might not even be true for matrices as well. So cancellation law that you have says 2x equals to 2y, so we can cancel this and say x equals to y, and this is something that we do a lot. But for matrices, if you have a times b equals to a times c, even though your matrix A is not 0, that does not immediately imply that b is equal to c. So these are the stuff that we all have to pay attention to when we are looking at matrix operations, because these are the things that are different. So we will look at more of this in your homework. And finally, in these particular sections in the textbooks, we also talk about operations such as transpose. This is pretty straightforward. So you have a matrix A. So your matrix A is of size, let's say it's 2 by 4. A transpose will be a matrix of size 4 by 2. What happens that is you take the row here and put it as a column here. You take the column here and put it as a row here. So you interchange that row and column. That's the concept of transpose. Just look at your book. It's not something that is very difficult. And there's also another operation, which is if your matrix A is a square matrix, 2 by 2, for example, that is something that is called the trace of a matrix. The trace of the matrix is basically the sum of the diagonal entries of the matrix. So for example, you have matrix A, which is 2, 1, 3, 4. This is a square matrix, so that we can talk about the trace of a matrix. So the trace of the matrix will be 2 plus 4. These are known as the diagonal of the matrix if it is a square matrix. Otherwise, there's no such concept as diagonal. So this is the diagonal of the matrix, and you take this number and add up this number, and that's called a trace. So we have a transpose, we have a trace, we have matrix addition, subtraction, scalar multiplications, matrix multiplications, and there is one thing that we didn't talk about, which is division, right? So divisions is something that is a little bit special, and we don't really talk about division per se. We will talk about inverses of matrices, and that will be in the next sections. All right, students, that concludes our discussion on section 1.3, matrices and matrix operations. I will see you in the next video.